Welcome to OwlsPrep. This is CIE 9709, A-Level Maths, Paper 1, Topic 1.8, Integration. Differentiation breaks a curve down into its gradient. Integration runs the whole process in reverse, and as it does, it adds up the area trapped under the curve. This lesson is both sides, undoing a derivative, then measuring areas and volumes. Let's dive in. Integration is differentiation run backwards. Differentiation takes a function to its derivative. Integration goes the other way. Given the derivative, recover the original function. Since differentiating with the power rule brings the exponent down and drops the power by 1, integrating does the reverse. Raise the power by 1, then divide by that new power. So the integral of x to the n is x to the n plus 1 over n plus 1 plus a constant c. Here n can be any rational number. With one exception, n equals minus 1 doesn't work because the denominator would be 0. That case belongs to paper 3. Why the plus c every time? Because a constant differentiates to 0, so the original could have ended in any constant, and integrating you have to put it back. For a linear inside, like bracket ax plus b to the n, you also divide by a. And paper 1 uses neither integration by parts nor substitution, and doesn't integrate trig or e to the x. Those are all paper 3. That constant c isn't just decoration. Given enough information, you can pin it down. Here's the classic type. A curve whose derivative dy/dx equals 2x plus 1 passes through the point 1, minus 2. Find its equation. Step 1. Integrate. 2x plus 1 integrates to x squared plus x plus c. Step 2. Substitute the point x equals 1. Y equals minus 2 gives 1 plus 1 plus c equals minus 2. So c equals minus 4. The curve is y equals x squared plus x minus 4. On the graph, curves with the same derivative form a whole family, just shifted up and down. The given point selects exactly one of them. So far, every integral carried a plus c. That's an indefinite integral. A definite integral is different. It's evaluated between two endpoints and gives a definite number. It's written as the integral from a to b of f of x, dx. To compute it, integrate to get capital F of x, then work out f of b minus f of a, the upper limit substituted in, minus the lower limit substituted in. And notice the constant c cancels in a definite integral, so you don't write it. For example, the integral from 0 to 2 of x squared dx. Integrate to x cubed over 3, then 2 cubed over 3 minus 0, which is 8 over 3. The most important use of a definite integral is finding area. The area between a curve and the x-axis, from a to b, is just the integral from a to b of y dx. For the area between two curves, integrate the top one minus the bottom one. The integral from a to b of y top minus y bottom dx. For example, the line y equals x plus 2 and the parabola y equals x squared meet at x equals minus 1 and x equals 2. So the area between them is the integral from minus 1 to 2 of bracket x plus 2 minus x squared dx. One caution. If a region is below the x-axis, its integral comes out negative, so mind the sign. The last application is the volume of a solid of revolution. Take the region under a curve and spin it one full turn about the x-axis, and it sweeps out a solid. Its volume is pi times the integral from a to b of y squared dx. The key is that square, because every cross-section is a circle, and a circle's area is pi times its radius squared, with the radius being y. So the volume is pi times the integral of y squared. Rotating about the y-axis works the same way, with pi times the integral of x squared dy. The easiest slip is forgetting to square the y. Remember, in a volume the y is always squared. So that's topic 1.8, integration, in 4 ideas. 1. Integration reverses differentiation. The integral of x to the n is x to the n plus 1 over n plus 1 plus c, with n not equal to minus 1. 2. Use a known point to pin down the constant of integration. 3. A definite integral from a to b equals f of b minus f of a, with no c. 4. Use definite integration for area between a curve and an axis, or top curve minus bottom curve. And for the volume of revolution, pi times the integral of y², never forgetting the square. And that is the final topic of Pure Mathematics 1. Congratulations, you've now been through all of Paper 1. See you at OwlsPrep.com.